I guess we've seen a great example of a stabilizer code, the Shor code, which is kind of just this way of encoding a single logical message qubit into 9 physical qubits where we can measure these 2 X stabilizers, 6 Z stabilizers, and then we can detect and thereby correct any single qubit Pauli error. In particular, we can correct any X error and any Z error. And in turn, we can correct any Pauli error and thereby correct an arbitrary single qubit error. And actually, it was pointed out to me in the break that the fact that we can correct X and Z errors, in this case, it should imply we can correct Y errors because kind of our X and Z stabilizers are totally independent. We have no like Y stabilizers. If you do have Y stabilizers, you actually might need to be more careful, but we won't really get into that today. All the stabilizers we'll see will only consist of tensor products of Pauli X's or Pauli Z's. So we can now generalize this idea of measuring stabilizers to have like a very generic framework for constructing quantum error correcting codes called stabilizer codes. And this is just kind of a general framework, a general language for doing what we've already been doing. So a stabilizer code is just a subspace Q of our 2 to the n dimensional complex vector space. And it's defined as essentially the set of all quantum states, or 2 to the n dimensional vectors, that are, literally stabilized by a set of stabilizers. So what that means is that we have some set, which I'll write here as script S. So we have a set script S of stabilizers, which is just any set of n qubit Paulis that are commuting. This one? This? Oh, sorry, this is just a script S. It's a very badly drawn S. Yeah. Actually, maybe I'll write it like this. So we just have some set, like here I'm writing like, I guess, bold S, of commuting n qubit Paulis. And our code, the set of code states is just, as we saw with the Shor code, it's the set of all states that lie in the +1 eigenspace, or are preserved by all of these stabilizers, all of these Paulis. And why do we want these stabilizers to be commuting? Essentially, if we have 2 non-commuting Paulis, then if we measure one and then measure the other one, if we go back and try to measure the first one again, we might actually get a different answer. Essentially because if these Paulis don't commute, the measurement outcomes will change when we kind of swap the orders around. And if you checked for the stabilizers we had for the Shor code, all of the Paulis commute with each other. So essentially, it doesn't matter what order we do the stabilizers in. We can kind of measure all the stabilizers in any order, and we'll get a well-defined syndrome, and then do our error correction. So in general, to correct errors, we just measure stabilizers. This gives us a syndrome. And then from this syndrome, we try to infer which Pauli errors occurred. Which Pauli error occurred. And if we can infer which Pauli error occurred, we can just apply this Pauli error again to revert the effect of the error. And of course, this syndrome measurement step is the step that collapses also non-Pauli errors into Pauli errors, which is this point we saw at the end of the first half. So in general, we want to kind of characterize how good is a quantum code, how many errors can it correct. And we can characterize the important properties of a quantum code basically with 3 parameters. So we say that our quantum code is an n, k, d code where n is called the length, k is called the dimension, and d is called the distance so the length is just the number of physical qubits, like the Shor code was a length 9 code. The dimension k is the number of logical qubits, or the length of the message. The number of message qubits that we encode into our code. So for the Shor code, k was equal to 1. And the distance d is the minimum weight of what we can call like an undetectable error. Undetectable error. So the distance is essentially the minimum number of qubits that we need to act on with some operator, such that after applying this operator, we've mapped our code state to a different code state. But since the resulting thing is still a code state, our syndrome measurements won't pick up on it. So it's kind of the minimum number of qubits we need to corrupt to cause an error, to change our underlying code state without being able to detect this error with syndrome measurements. And it turns out that kind of by this reasoning that we can always collapse errors to Pauli errors, it suffices to look at Pauli errors when computing the distance. So the distance is actually also equal to the minimum weight of a Pauli that commutes with all stabilizers, but is not itself a stabilizer. So of course, if we apply a stabilizer to a code state, we get back the same code state. So stabilizers don't cause errors. So essentially, to find the minimum weight of an undetectable error, we want to find the minimum weight of a Pauli operator that's not a stabilizer. So it indeed is causing some sort of error. But we also want this Pauli to commute with all the stabilizers, which that's equivalent to saying that our stabilizer measurements don't pick up on this error. Our syndrome will be all plus ones even after applying this Pauli. So this is how we can compute distance. And we've basically seen this, but I'll kind of leave it as an exercise to verify all the details, that the Shor code is a 9, 1, 3 code. So it has length n, dimension 1, and distance 3. And this might sound a little weird. I said we saw the Shor code could only correct a single error. Why is the distance 3? It turns out that you can only essentially, if you have errors occurring in unknown locations, you can only correct a number of them equal to roughly half the distance. So I'll also leave it as an exercise to show that if we have a code of distance d, stabilizer code of distance d, then we can correct, or I guess detect and thereby correct, d minus 1 over 2 errors in unknown locations. So if we have an error in between, like an error of weight bigger than d minus 1 over 2, but smaller than d, what that's saying is that if we measure the syndrome after this error occurs, we'll pick up something. Our syndrome won't be all +1s, so we'll see that an error occurred. But there might be multiple different errors that could have caused this particular syndrome we observed. So we won't be able to uniquely identify like what error occurred in order to correct it. So if we actually want to uniquely identify the error well enough to correct it, we need to assume that the number of errors that occurred was only half the distance. And it's an exercise in the problem set to kind of show that this factor of 2 is kind of all the slack you need to go from detecting errors to correcting them. Are there any questions just with the basic definitions here? Yes.
So when you define the stabilizer code, here you don't consider the sign of the polys, right? You're just talking about polys without sign.
The sign of the Pauli is like
plus minus.
Oh, like if we have like plus x, y. Yeah, exactly. So yeah, so maybe here we're not, depending on how you define Pauli's, like whether you include the phase in front or not. Yeah, here we're not really including the sign side. So we're just like saying take I, x, y, z, and just take tensor products of them. Yes?
Can we say the other way, like if a code can correct d-1/2 errors, can we say it is a distance decode?
Yes. You can also go the other way. Yeah, that's also a good exercise to show. Yeah, there's actually a more general characterization called like the nil-Laflamme conditions, which characterize kind of exactly if you can correct some set of errors, then you can also detect kind of essentially, if there's a set of errors you can correct, then essentially if you multiply any two together, get something you can detect, which is kind of intuition. But it does go both ways. Yes?
So can we define codistance in another way, such as the minimum weight Pauli that forms a bounded logical operations?
Yes, and we'll actually do that in a minute or two. Okay, great. All right, so maybe I'll say this is kind of if and only if. Right, so getting to that point of logical operations. So to motivate this, there's something that we haven't talked about at all yet, but is actually a very important problem in practice, which is if someone gives us a code state, we've seen how to correct errors on it, but we haven't actually seen how to identify like where is the logical information, where is our logical qubit encoded inside, say, these 9 qubits in the shortcode. Or maybe even more ambitiously, say someone hands us a 9-qubit shortcode state, and we want to perform a logical bit flip. We want to say, perform like a logical, essentially perform a Pauli X on our encoded message, but without decoding, performing the X and then re-encoding. Because if we decode, we kind of lose our error correction capabilities. So how can we identify the logical qubit? And explicitly, how can we perform like a logical bit flip, which I'll denote as kind of X with a bar over it. So an X operator on our encoded or logical qubit, or a logical phase flip. So I'll denote as Z with a bar over it. And if we go back to the shortcode where logical 0 state is 0, 0, 0 plus 1, 1, 1 over root 2, tensor 3. Logical 1 is 0, 0, 0 minus 1, 1, 1 over root 2, tensor 3. Then for a logical bit flip, it's at least clear what we want it to do. We want it to map the logical 0 state to the logical 1 state, and the logical 1 state to the logical 0 state. So does anyone see a valid choice, maybe an n-qubit Pauli operator, a product of Pauli's, that has this effect, that maps logical 0 to logical 1 and logical 1 to logical 0? Combination of z's. Do you have a suggestion for which ones? So 1, 2, 3. So let's see. So we apply 1, 2. If we apply 1, 2, 3 to this state, what happens? Well, nothing happens to the zeros, and we get 3 minus signs. So what that will end up giving us is, so Z1, Z2, Z3, and 0. So we get 3 minus signs, which is equivalent to 1 minus sign over root 2. But then the other 2 copies, we haven't done anything yet. So we'll still have a plus. Yep, great. Perfect. So if we do Z1 all the way through Z9, we can see in all 3 triples, we're going to essentially flip the sign. And we've mapped our logical 0 state to a logical 1 state. So we want to set our X logical operator to be a product of Z is acting on all 9 qubits.
Question, can I just act on Z1, like Z4, Z7? Just
Yes. Great. So you've already observed something kind of interesting, which is that this isn't a unique choice. We could equivalently have just done Z1, Z4, Z7. And that would also have the effect of flipping the sign in each of these 3 triples. So that's another valid choice of our logical X operator. So I'll write like this is kind of equivalent. And in fact, there's many valid choices, but any 2 of these valid choices will differ by a stabilizer, or differ by a product of stabilizers. So essentially, if we take Z1, Z4, Z7, and then multiply it by, say, the stabilizers Z2, Z3, Z5, Z6, and Z8, Z9, we get Z1 through Z9. So essentially, logical operators are only well-defined up to stabilizers. Or another way of saying that is that we have a lot of different representatives for every logical operator. We can take any given representative, then multiply it by any stabilizer, and we get another valid representative. Boy. So we have logical X. We can also write down a logical Z operator. We want logical Z to act on the 0 state by doing nothing, and act on the 1 state by flipping the sign. So Z applied to logical 0 is 0, Z applied to logical 1 is -1. And just like we saw, logical X in this case was a product of Z's, it's going to turn out that logical Z is a product of X's. So we can actually just check that if we set logical Z equal to x1, x2, x3, I mean, what does that do? It does, on the logical 0 state, it just flips zeros and ones, but there's just a plus sign there, so it does nothing. On logical ones, when we do x1, x2, x3, we flip 0, 0, 0, minus 1, 1, 1 to 1, 1, 1, minus 0, 0, 0, which just flips the sign. So logical Z will just flip the sign of the 1 state and do nothing to the 0 state, which is exactly what we wanted. And again, we can multiply this by any stabilizer, and we'll get another valid representative of logical Z. Oh, so we have a logical X and a logical Z operator. They tell us how to perform bit and phase flips on our encode qubit without decoding. And we can ask, like, how do we do arbitrary single qubit gates? And just like kind of with error correction, where we saw that, at least for the short code, it's once we know how to correct x and z, we can correct any error. In general, once we know how to do a logical x and a logical z, logical bit and phase flip, we can use these to essentially generate arbitrary logical operations on our logical qubit. Right, and so it turns out that in general, if we have a pair of anti-commuting operators, x bar and z bar, we can think of them here as being like n-qubit Paulis, but in full generality, that might not even be necessary. So in particular, since they're Paulis, they square the identity. This gives us a logical qubit. Now, why is it sufficient to have a logical x and z operator? Essentially, we know that y is I times x times z. And then we also saw before that every single qubit operator, every 2x2 matrix, lies in the span of I, x, y, and z. So the logical version of any 2-qubit operator, acting on a logical qubit, so any single qubit logical operator should lie in the span, or should be a linear combination of I, x bar, y bar, and z bar. So essentially, once we've found x bar and z bar, we know how to do, we can take linear combinations and do arbitrary single qubit operators. Yes?
So to be able to perform these or define these logical operators, they have to cover a distance greater than d, right?
Yes.
So anything that has a distance less than d, it doesn't destroy our state, and greater than d destroys our state.
Yes, so this is a great point, and we'll do that explicitly in a second, but that's exactly right. Anything of weight, or I guess maybe you want to say d by 2, depending on,
Right, yeah.
but yeah, so anything of weight, any Pauli of weight less than d by 2, oh no, I think, so any Pauli of less than weight d by 2 we can correct, but you're definitely correct. Any Pauli of weight less than d cannot be a logical operator.
Right, yeah.
Yeah.
And can you give an example of a Pauli, for example, for the short code that commute QL stabilizes, but it's not a stabilizer?
Yes. Yes, thanks. So I guess we can claim that this would be an example of an operator that commutes without stabilizers but is not a stabilizer.
And okay, but it has a weight greater than d, so that's not.
Yes, so it's not contradictory. And this is actually another example. So both our logical x and z are,
Okay, I understand, because it says minimum weight, so these are, okay.
yeah, as long as they're greater than that. Yes.
Since we know like how to do logical X and logical Z, I just wonder how can we do like logical T gate? Because I don't think you can decompose it to X and Z.
Oh, yes. Oh, wait. I think we can decompose T into I and Z. So, I don't know if you can see. I guess T is like 1 e to the I pi over 4, 0, 0. And I think I claim that that's some coefficient times identity plus some coefficient times Z. there's some coefficient here and some coefficient here.
But you don't really do linear combination on the circuit, right? You just multiply one after the other.
When you apply the gate, you really do like multiplication rather than subtraction, right?
You do multiplication. Oh yeah, so right, so we will literally have to take like logical x and z and literally take like some coefficient, like some alpha 1 times x bar plus some alpha 2, or in this case it would be alpha 1 times I plus alpha 2 times z bar. And we would want to, so this is a well-defined operator. And the claim is that this is the type of thing we would want to apply.
Yeah, because I'm wondering how do you translate into like single qubit operation out of this, right?
Oh, like how do we implement this?
Yeah.
Yeah, so there's no obvious way to implement this in practice because this is just some weird operator acting on all 9 qubits. And hopefully, depending on time, by the end of this, near the end, we'll see some ways to like do T-gates and kind of T-gates maybe using like single qubit operations or something. But yeah, I agree. Like for the Shor's code, there's no obvious way to implement a T-gate without doing some arbitrary, difficult unitary on all 9 qubits at the same time. Yes.
So if we know what the logicals are, physically, we can imagine just do the rotation, right? So the exponential. It's gonna translate to some like multi-body like entangling operation, but like that can like answer this question. Right?
Oh, right. You're saying like we can take exponentials of these Paulis. Yeah, exactly. Yeah. So right. So as another, essentially, once we have these Paulis, we can generate arbitrary logical gates based on them. I guess by exponentiating, for instance. But yeah, there will be some like arbitrary 9-qubit unitaries that look kind of ugly. And yeah, eventually we'll want to find more natural ways to do these uncode states, like in a fault-tolerant manner. Was there a question in the back? Oh, yes.
My original question was just concerning like logical Hadamard gates and like T gates like that. But there's already a question asked.
I see. Oh, wait. Yeah, so we'll later see that kind of, this is a very unsatisfactory way. I think what a lot of people are saying is this is not a satisfactory way of doing arbitrary logical operations. And if there were an easy way to do that, kind of quantum error correction, quantum fault tolerance would be a lot easier. So like, it is indeed a difficult thing to do to like find good ways of doing logical gates on our code states. And by good here, I just mean ways that kind of don't act on like all the qubits in some very difficult to apply circuit. All right, so just to kind of formally write down our definition. So for a stabilizer code, a logical qubit, or we can also call it like a logical operator pair, of a stabilizer code is just a pair x bar z bar of anti-commuting Paulis anti-commuting n-qubit Paulis that commute with all the stabilizers. That commute with every stabilizer. And again, the condition that our logical operators commute with all the stabilizers just ensures that they preserve the code space. Essentially, if our logical operator were to anti-commute with some stabilizer, then after applying the logical operator, that stabilizer, when we measured it, we would get -1. So we would have left the code space, which means that's bad. That means we're not preserving the code space. So we commute with all the stabilizers, and then anti-commuting is just because kind of Pauli X and Pauli Z anti-commute with each other. And that anti-commuting in some sense gives us our logical qubit. So we have this definition. For the short code, we've seen examples of logical operators. We've seen that for logical X and logical Z, for each of them, there's multiple choices. We can multiply by stabilizers and get equivalent representatives. The one additional thing we want to figure out how to do is actually, how can we find these logical operators in general? Go over here. Yes.
So to retroactively find the coefficients of the unitary in terms of the Paulis, you would need to, I guess, have them be have the span be part of like inner product space. So is it like a trace inner product or?
I see. Oh yeah, you're saying how do we get this decomposition, like of T-gate, for instance?
Yeah, it would have to be like an inner.
Yes. Yeah, exactly what you're saying. Yeah, we can take inner products using the trace inner product.
Okay, just check.
Yep. Exactly. Okay, so how do we find logical operators? So let's say we're given some stabilizers, S1, S2, and so on. And I'll just kind of draw visually kind of our process for finding logical operators. Essentially what we're going to do is we're going to find them one by one. We're going to repeatedly find an operator that commutes with all the stabilizers. We'll just call that a logical X. We'll then find something that anti-commutes with it, call that logical Z, and then just repeat. So this won't be kind of actually, in this tutorial, we won't really see specific examples of codes with more than one logical qubit. So this won't be super important, but kind of in general, eventually we want codes with higher dimension. And then you really do need to be able to find these things. So let's say this box represents a set of all n qubit Paulis. So there's, I guess, 4 to the n vectors in here. So each, you can just imagine this is a bunch of points. Each one is like some tensor product of i's and x's and y's and z's. And if we say just look at our first stabilizer, that kind of cuts this space in half, where everything to the right of this line commutes with our first stabilizer, S1, and everything to the left anti-commutes with S1, because every pair of Paulis either commutes or anti-commutes. So S1 cuts this in half. We have the commuting side and the anti-commuting side. S2, again, will cut this in half. Everything above this line we can think of as commuting with S2. Everything that below this line anti-commutes with S2. And we can keep on going until we've kind of taken all of our stabilizers. If we have like K stabilizer, or R stabilizer generators, we'll cut this space in half R times. Here I'll just assume we only have 2 stabilizer generators. So kind of this quarter here is the set of all Paulis that commute with all of our stabilizers. And what that means is that we can actually just choose any point in here that's not a stabilizer. So all of our stabilizers will lie in this point, will lie in this quarter, because stabilizers commute with themselves. If we choose any point that's not a stabilizer, we can just label that to be x bar 1, our first x logical operator. And again, x bar 1, if we now look at commuting versus anti-commuting, that cuts this quarter in half. We have the things that commute with S1, commute with x1, and we have the things that anti-commute with x1. And we recall we want to choose z bar 1, our first logical z operator, to anti-commute with x bar 1. So we choose z bar 1 to be an arbitrary element of this box here. And now we found a logical qubit. So we found a logical qubit x bar 1, z bar 1. And then to find more logical qubits, we can just repeat. So we look inside this small box, consisting of things that commute with all of our stabilizers and commute with x bar 1. And we can take things that also commute with z bar 1. So we can use z bar 1, cut this in half again. And then we just repeat. We find like an x bar 2 that commutes with all of our stabilizers and commutes with our first two logical operators. We use that to cut it in half again, and we find a z bar 2, which anti-commutes with x bar 2, but commutes with everything else. And we just keep on going. And we keep going until essentially the only thing left in this tiny region is stabilizers. And once there's only stabilizers left, kind of we can't find any more logical operators. So at some point, we'll hit some x bar k, z bar k, and we can't find any more logical qubits. Yes?
Good question. Why must the logical gates commute with the stabilizer?
Yes, great question. So,
Repeat this good question.
sorry?
Why must the logical gate commute with all stabilizers?
Yes, so I completely glossed over this. So why did we define this? So we want logical operators to preserve the code space. We want them to map code states to code states. And you can actually check that if we have an operator that doesn't commute with some stabilizer, that means that if we apply that operator and then measure the stabilizer, if it anti-commutes, we'll actually get a -1 from this measurement. And in general, you can convince yourself that any Pauli operator that commutes with all stabilizers will map code states to code states. And I can just write down a really quick proof. So say we have like logical x bar, and it commutes with all the stabilizers. Then we want to show it preserves the code space. So we want to show that logical x bar times any code state is itself a code state. What does it mean to be a code state? It means that we're preserved by stabilizers. So we want to show that any stabilizer times x bar times psi bar so we want this to equal just x bar times psi bar. If this is true, then we're a code state. But yeah, exactly. We just commute x bar in our stabilizer. And then we know that stabilizers do nothing to code states. So essentially, this state is equal to this state. Great. Yes.
How do you choose the stabilizers to start with?
Oh, yes. So that is the hard part. Here we're assuming we're given a stabilizer code, and we're saying, how do we find the logical operators? But actually, constructing the stabilizers, or defining the code, is kind of one of the hardest parts of quantum error correction. For the short code, we saw how we can do it by essentially concatenating two repetition codes. In a little bit, we'll get to the surface code, which does it. It constructs stabilizers in a different way, almost from like a topological viewpoint. But if we had a really good way of doing this, we would, in some sense, like solve quantum error correction. So.
But you can start with any set of stabilizers, so there are some properties you have to satisfy.
Yeah, we just need them to commute with each other. So essentially, so that we can measure them all simultaneously without like any conflicting measurements. But any.
What's the implication? It's a larger set, a smaller set. How does it matter for the code efficiency?
Right. So actually, we'll see that we'll see a little bit more about that, but essentially, the more stabilizers we have, the more constraints we impose on our code. So generally, we'll then have fewer logical qubits, or like a shorter message. We'll also be able to correct more errors, because we're kind of doing more measurements. We have more opportunities to detect errors. So if we want very good, kind of to correct as many errors as possible, we're going to want a lot of stabilizers. But then we can only encode, in general, we could only encode fewer logical qubits. So there's kind of a trade-off there. Yes?
If the logical X and Z operator only need to commute with all the stabilizers, it seems I can replace one of the stabilizers with the logical X or logical Z. What if I do that? In the case of short code, maybe the code distance will decrease, but in general, what will happen if I just exchange them?
Right, replace the stabilizer with a logical operator.
Yeah, replace say S1 with logical X, and let S1 be my logical X.
I see. So I think something might go wrong, which is that each of these operators commutes with all the stabilizers. So each of these commutes with all of these. All the stabilizers commute with themselves. The only things that anti-commute are these two anti-commute, these two anti-commute, and so on. These two anti-commute.
Yeah, I mean, I define my stabilizers as S1, S2, and X1, and the last S will be my new logical X, and I find another anti-commute with another operator anti-commute with the new logical X.
I see. So you're saying like we add this as a stabilizer, we get rid of this, and then we still keep these logical operators?
Yeah, and one of the original stabilizer will become my new logical operator.
Oh. I see. Yeah, so I think you can do this. I don't think there's a general like formula for how this will affect the like parameters of the code, like the distance and dimension. Kind of as we'll see, especially with the surface code, often we choose stabilizers to be very low weight, to act on like as few qubits as possible, because that makes them easier to measure. Whereas logical operators, we want to be kind of longer, because kind of the distance of the code is like the minimum weight of a logical operator. So often we probably wouldn't want to do this because we want our stabilizers to stay low weight and our logical operators to stay high weight. But yeah, in general, you definitely could do it, and maybe in some cases it might improve the parameters. I'm not sure.
Yeah, and what if I exchange my logical X with logical Z? Because you said logical X and Z, they need to anti-commute, but they both commute with all the stabilizers. So if I exchange them, they still satisfy this condition. But that in the case of short code, it is still correct if I use X1, X2, X3 as my logical X and the other.
Yes, that is also a great point. And this is kind of, what you're saying is a special case of, or maybe I can just rephrase what you're saying in that there's multiple valid choices of a basis for our logical operators. So we could have just as easily, instead of like x2 bar, z2 bar, had z2 bar, x2 bar. So swap the logical x and z. And this essentially gives us the same code. We've essentially just changed the basis for our logical operators. It's almost like we've just applied a logical Hadamard gate to the second logical qubit. We could even like multiply together. We could like multiply together different logical operators to make more logical operators and find just a totally different basis for these logical operators. And so in some sense, this is like writing down one basis for our k logical qubits, but there's many valid choices for that.
Just to clarify, your x2 bar need to commute with all the stabilizers and the x1 bar, right?
Yes.
And then what about the z2? z2 need to anti-commute with the x2 bar. And what about the z1 bar?
Oh yeah, so each zi bar anti-commutes with xi bar and commutes with everything else. So like z2 bar, it anti-commutes with x2 bar, but it commutes with all the other zis and xis and all the stabilizers.
I see. Actually commute, not anti-commute with the other x.
Yeah. Okay. Sorry, back and then we'll move up.
Is there any, can we set a bound on the value of k based on the value of n? Like, depending, in some form, like how many qubits we have here?
Yes. Great. So let's say that we have the number of stabilizer generators is r. It's going to turn out that we're going to run out of new choices at exactly k is equal to n minus r. Essentially because every time we add another pair of logical operators, we cut our space in half 2 more times. So if you just count, so we start with like 4 to the n Paulis, because there's 4 Pauli matrices. So if you count how many times we've cut in half, essentially after finding n minus r pairs of logical operators, all that'll be left in this corner is just the stabilizers. Yes?
Once we found x1 Z1. Why do we need to look for more? It's because we have a logical base. And I'll ask a follow-up after that.
Oh, yeah, so great. So finding more. So with the shortcode, we actually can't find more. But ideally, eventually, we'll have codes that can encode more than one logical qubit into a code block. So if we have both x1 bar, z1 bar, and x2 bar, z2 bar, then we could, in theory, combine them and do like 2 qubit gates between them. And essentially make use of multiple logical qubits.
Okay. Because the second part was like, are those sets of logical gates independent of one another, which it seems like they are, because x2 just commutes with everything other than z2.
Yes.
So are they like in different bases? They're still the same bases.
Yeah, so what we can think of this as is, if we imagine unencoding everything, then we just have k qubits. And on k qubits, we just have bare like non-logical, just physical Pauli operators like x1, x2, and all the way up to xk. And then z1, z2, all the way up to zk. And so just on k ordinary physical qubits, we have these kx Paulis and these kz Paulis. And essentially, we're just doing our code is just doing a basis change and mapping kind of ordinary Paulis to these like logical Paulis. So I don't know if this is answering your question, but kind of anything we could do on k ordinary qubits, we can now do on k encoded qubits using these logical operators.
And will it also be k sets of gates? Like for short code, for example.
Oh, so for sure, k equals 1.
Yeah.
But yeah, for other codes, we could have larger k. Yes.
Yeah, given the stabilizers, can you find the errors that it can correct?
Given this,
Code can correct.
sorry, given the stabilizers.
Can you find the errors your code can correct? Like which codes, which set of errors it will correct?
Oh yeah, so yeah, exactly. The stabilizers always determine which errors we can correct. The logical operators, they don't really have to do with error correction as much. So yeah, the stabilizers are what does that. The logical operators are more how can we like identify the logical qubits within the code block. Yes, and then.
So you said that as we increase the number of stabilizers that we define, the number of logical operators reduce. Is it the combination that we are like having the logical operators that reduces?
The combination of.
Like how, we can have multiple ways in which we define logical X and logical Z. That reduces?
Oh, sorry. So, no. Oh, sorry. Sorry, I should have been more clear. So the number, like the k we can find, the number of pairs of logical operators that anti-commute within the pair but commute across, this k will decrease as we increase the number of stabilizers.
So this K is the number of ways I can define my logical operators, right?
I would say it's kind of maybe the number of independent, like the number of logical qubits encoded in your code, or the number of kind of independent pairs of logical operators that you can find. So there's, sorry. Oh, wait, sorry. So maybe part of the reason this is confusing is that we've only seen the shortcode where there's a single logical qubit. So like the shortcode encodes 1 qubit into 9 qubits. But in general, we could have a more general code that encodes like 2 qubits into like 20 qubits or something. And so in this case, so in the shortcode, we just had x bar and z bar for like x and z on our single message qubit or single logical qubit. If we have a code that encodes 2 qubits into 20 qubits, we need to figure out how to do a bit flip on both the first message qubit and on the second message qubit. So we need a logical x1, which is bit flip our first logical qubit, and a logical x2, which is flip our second logical qubit. So each of these pairs is kind of acting on a different logical qubit.
And when we say that as we increase the number of stabilizers, there are fewer errors that will happen. So can we relate that to the distance as well?
Oh, yes. So, right. So as we increase the number of stabilizers, in general, we'll be able to correct more errors and our distance will rise. You can write down examples where like you have a lot of stabilizers but still your distance is very bad. But yeah, in general, to achieve higher distance, we will need more stabilizers. Yes?
Given a logical circuit with k logical qubit with a fixed set of stabilizers, and there are at least k factorial and 2 to the power of k numbers of different assignments of logical operations. And how do you know this is astronomical, and how do you find the optimal labeling or optimal assignment of logical qubit to a logical circuit you want to compile?
Yeah, so I think that's a difficult problem in general, like what basis to choose for these logical operators. I don't think I really have much to say about the general case. But yeah, in specific instances, I guess you can try to optimize this. But I imagine it's a hard problem. Yes?
In general, when you're dealing with logical qubits and logical operations, do you have no use for the anti-commuting regions of your subspace?
You have no use?
No use for the anti-commuting regions?
Right, so these are the regions. We can kind of think of them as regions we get mapped into when errors happen. Because when error happens, then we start anti-commuting. Yes?
Given K, is there like a hypothetical most optimal Q? So given K, can we define the most optimal physically possible n distance to get like the theoretical best error corrected code?
Yes. You said the optimal Q? Or sorry, what is? Oh, yes. Sorry, yes, Q is the code, of course. Thanks. No, this is a great question. And so in particular, we can ask, we have the NKD parameters. We can ask, like, what are the optimal NKD parameters for, like, how do they trade off with each other? Like, say we choose R to be n minus k, so we can kind of just choose that, given the number of stabilizers. And maybe what's the optimal distance? It turns out that optimally, our distance is always at most something like n minus k, I think plus, I may be getting this +1 wrong. But it's always at most something like n minus k plus 1 over 2. So essentially, if we have k logical qubits, meaning we have n minus k stabilizer generators, then the number of errors we can detect is at most like roughly n minus k over 2. And there actually are codes. So there are codes that achieve this bound if we move away from qubits to systems of higher local dimension. For qubits, you can actually prove stronger bounds than this. But yeah, achieving this bound it's not too easy to do. Yes?
Sorry. You said earlier when I had asked the question that you need these other pairs of logical gates to be able to form 2-qubit gates. And I was wondering why, but is it because you want x1 and x2 to be able to address each qubit individually and not with both at the same time?
Yeah, exactly. Yeah. Oh, yes?
If we want to find like logical 2-qubit gates, say like the CNOT gate, will we have like similar procedure? Like,
right, so yeah, so I'd say in general we saw you can decompose a single Pauli operator into a linear combination of, a single qubit operator into a linear combination of Paulis. We can decompose like a 2-qubit operator into a linear combination of 2-qubit Paulis. So any like 2-qubit operator can be written as some coefficient times I tensor I plus some coefficient times I tensor x plus and so on all the way up to like z tensor z. And so like if we just replace all the physical Paulis with logical, right, so we don't need to do it for I, we can only see that in theory we have like a well-defined logical CNOT gate. It'll decompose somehow. Actually doing this, like finding an explicit circuit to do this is another question. But. Yes?
I couldn't really hear you properly, but you were saying that for qubit codes, that bound hasn't been achieved? Or is that because it just hasn't been discovered, or is it because there's a more strict theoretical bound?
Oh yeah, so there is a strict, so this is called the singleton bound. And there are stricter bounds I don't remember what they are, but there are stricter bounds that apply to codes on qubits. So yeah, this constant here can be improved. Oh, great. So I guess we'll try to move on. And we've now essentially seen all the background we need on stabilizer codes to start talking about better stabilizer codes. So everything we've seen so far, we've essentially seen the repetition code and the short code. It encodes a single logical qubit, and it can correct against at most one error. The short code can correct against any single qubit error, but we still can't correct, or we still can't detect and then correct like more than one error in an unknown location. So how can we correct more than one error in an unknown location? A very simple idea to do. Or equivalently, we want maybe distance greater than 3, because we saw the short code is distance 3. A very simple thing we can do is just kind of remember how we constructed the short code where we concatenated 2 repetition codes. And actually just keep on concatenating, but now we can just concatenate the short code directly. So we can start with our single message qubit, encode it into the short code. So that's like a 9-qubit code. This gives us 9 physical qubits that we can then take each of these physical qubits and encode that into another short code. And we can actually keep going. We now have like 81 qubits here, 9 groups of 9. We can encode each one into another short code. And we can do this for an arbitrary quantum code Q. So we can this is called like concatenation. We can get Q concatenated with itself. We can get Q concatenated with itself, concatenate with itself again. And it turns out that if Q is an NKD code, then Q concatenated with itself will be an n squared, k squared, d squared code. Q concatenated with itself 3 times will be an n cubed, k cubed, d cubed code. And actually, k equals 1 here, and it's a little unclear to see how to deal with more than one logical qubit. So let's just say Q is an n1d code. Then we get n squared 1d squared, n cubed 1d cubed, and so on. And I left it as an exercise in the problems to prove that the distance, kind of the distance gets multiplied by d every time you concatenate with a distance d code. But essentially, this shows us how to grow the distance and thereby grow the number of errors we can correct. Yes?
Sorry, can you not encode one qubit in more than 3 qubits to increase that?
To increase
Distance.
the distance?
Yeah, like, because here we're putting one qubit into 3, right? 0 goes to 0, 0, 0. 1
Oh.
goes to 1, 1, 1. So can we not do 5 or 6?
Right, yeah, so
Or is that worse than doing this?
I see. Oh, you're saying just take the short code and like concatenate longer repetition codes.
I guess.
Or sorry, replace the short code with like with like a 5 by 5.
More, yeah, I guess like instead of having 3 blocks, you have 6. Right?
Yes, yeah, that works too. We could just start with. Yeah, so I think asymptotically. So here, asymptotically, the distance grows as roughly the square root of the block length, because here, like if we start with the short code, we start with 9, 1, 3. And if we just square 9 and 3, we'll end up with like 9 or 81, 1, 9. I think what you're suggesting will also have the distance growing roughly as the square root of the block length. So at least in terms of NKD, they'll have roughly equivalent performance. One advantage of kind of this repeated concatenation is that it turns out that, so in both cases, you'll notice that the stabilizer weight is growing. And with repeated concatenation, we'll actually end up with more low weight stabilizers, somehow because from this inner code, this last level of concatenation gives us a lot of low weight stabilizers. So I'll postpone this discussion a little because we'll get into that more, but I'll say that there are reasons to do this, though there also might be cases in what you suggested might be better. So, great. So this is great, and actually, using these concatenated codes, we can, in some sense, do all the error correction we'd want to do. You can do like universal fault-tolerant computation, whatever that means. Essentially, kind of everything you could want to do with just concatenated codes. The one issue, or there's a few issues, maybe the major one, is that the performance in practice isn't great. Somehow, these concatenated codes, even asymptotically, if they look okay, there's some constant factors in front of the asymptotics and so forth, which make them perform not as well as some other codes in practice. Also, we've only seen how to encode a single logical qubit, like a single message qubit, into more. There are ways to adapt concatenation to improve that, but it's maybe not super obvious from this setup. And there's also this issue of low versus high weight stabilizers, which we'll at least touch on in a bit. But all of this kind of motivates looking for better codes. And in the remaining time, I guess we'll see at least one example of a code that seems kind of much more promising in practice, which is the surface code. I'm sure a lot of you have at least heard of it. It's still kind of one of the most popular codes in practice. So let's go to the surface code. So the surface code is actually a family of codes. It's a family of codes of length n, dimension 1, so one logical qubit, and distance growing as roughly square root of n. And the stabilizer weight is equal to 4, which essentially means that, like with the short code, we saw we had these stabilizers like x1, x2, x3, x4, x5, x6. That's a weight 6 stabilizer. For the surface code, every stabilizer has weight at most 4. So it's a tensor product of at most 4 Paulis. And that's actually very nice in practice because it means to measure any given stabilizer, we only need to interact with just 4 different qubits, which is obviously more efficient than trying to measure a very high weight stabilizer. So how do we define the surface code? We first draw a large lattice. Say it's like an L by L. I don't know if I drew the same number of rows and columns, but we can imagine this is an L by L lattice. And I've drawn it a bit funny. I've drawn kind of 2 different types of boundaries. So on the left and right, we have what are called smooth boundaries, where it's how you normally draw a grid. Whereas on the top and bottom, we have what are called rough boundaries, which means we have kind of edges hanging off without any vertices on the edge. This is actually intentional. In some sense, having these two types of boundaries are going to give us like our x and z logical operators. But okay, so we place qubits on edges of the lattice. So each edge here corresponds to a physical qubit. So the number of physical qubits is L squared plus L minus 1 squared. That's just the number of edges in this lattice I've drawn. We place X stabilizers on vertices. So essentially for every vertex is touching, most vertices are touching 4 edges. And so we can just define a tensor product of 4 Pauli x's, just x tensor x tensor x tensor x on these 4 edges touching the vertex. And we define that to be an X stabilizer. Similarly, like for every vertex, we just define an X stabilizer to be a tensor product of Pauli x's on the associated edges. And on these smooth boundaries, we actually only have 3 edges touching the vertices. So that corresponds to a weight 3 X stabilizer. We're then going to place Z stabilizers on the faces, or on the squares of this lattice. So essentially, for every square, we define a Z stabilizer, which is a tensor product of Pauli Z's on the 4 edges touching that square. So this is a Z stabilizer. This is a Z stabilizer. And we also have some weight 3 Z stabilizers along these rough boundaries, because this square kind of has no bottom edge. So we just have a tensor product of Pauli Z's on the 3 edges touching this like open-ended square. And we can check that every X and Z stabilizer commute. So these X and Z stabilizers commute. Essentially because if we zoom in and draw an X stabilizer, oh no, that is the wrong color. So we zoom into X, 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 X. And we zoom in on a Z, 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 Z. If we ever have an X and a Z stabilizer that overlap at all, they have to overlap at 2 qubits. Essentially because every square and every vertex share either 0 or 2 edges. And in general, it's just a fact that kind of Pauli X tensor X and Z tensor Z commute. So if we have an X stabilizer and a Z stabilizer that overlap at exactly 2 qubits, they must commute with each other. So for this reason, kind of all the stabilizers commute with each other, and we have a well-defined stabilizer code. Yes.
Still trying to visualize the qubits on edges. So how do you place it to bring it to number of L squared plus L minus 1 squared?
Oh, sorry, yeah. So I'm literally just counting, like, how many edges, 1, 2, 3, 4, 5, 6. If you just maybe do like a 3 by 3. So this is 3 by 3, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 13 is 3 squared plus 2 squared.
Oh, so potentially, qubit can correspond to 1 grid. It also can correspond to 4 grids together, or something like 2 by 2 grids.
Oh, sorry. So each qubit is just one edge.
Right.
So we have to choose the size of this grid. And that determines the number of qubits. So there's essentially, it's a family of codes. parameterized by the size of the grid. And yeah, once we choose the side length L, that determines kind of how many physical qubits we have, because we just draw this lattice and place a physical qubit on every edge.
Oh, right, yeah. Yeah, I think I got that now. I was mixed up the on the faces with qubit on the edges.
Oh, yes. Yeah, no, so people do, there are different conventions for how you draw this. The way I'm drawing it is qubits on the edges, z's on the faces, and x's on the vertices. Yes?
I'm just curious, so like I see in experiments that people usually prefer the rotated version of the surface code where the qubits are on vertices and it's a checkerboard pattern of x and z faces. And in that case, you can get away with half the data qubits, but the same distance. Is there any advantage that this picture has over that rotated picture?
Yeah, so in practice, I am not too familiar with the advantages of one or the other, though I think you're right, there's definitely some advantages of the rotated surface code. I think for understanding the properties, especially in like characterizing x and z logical operators, I just like the picture in this case more, but that's really all. Yes.
Or is it like everywhere and there's actually overlap throughout the grid as well?
Oh yeah, thanks. So everywhere, every vertex, I've only drawn some of them, but every vertex has an x stabilizer, every face is a z stabilizer, and they're overlapping everywhere. Yes?
Two questions. First question, I don't quite understand the surface code. Does like the vertex itself mean anything? And the second question is like, actually I forgot the second question.
Sorry, what was the first question? Do the
vertices mean anything?
All right, so the vertices, so physically we just have a qubit on every edge. So the vertices physically don't mean anything, but to do error correction, we kind of associate a stabilizer to every vertex. So the vertices are just they kind of index, they give us a way to index our stabilizers.
Oh yeah, I remember my second question now. Like, does putting like the x and the gate on like the, are they to form like the logical gates?
Yes, we'll see that in a second.
Is there a reason for not considering like both rough edges or both smooth edges?
Oh, like having like rough all the way around?
Or both smooth all around?
Okay, we'll also see that when we look at logical operators. Oh, great. So, right, so we want to find our logical operators, and really if we just want to compute, like this is an NKD code, I claim these are the parameters. We already saw that K is the number of pairs of logical operators, and D is the minimum weight of a logical operator. So we really want to compute our logical operators. And what is a logical operator? Well, it's something that commutes with all the stabilizers, but is not itself a stabilizer. So for instance, a logical Z operator is a product, like a tensor product of Pauli Z's that commutes with all the X stabilizers, which means that it has an even size intersection with every X stabilizer. Or with, I guess, so an even number of Z's, or as even number of edges touching every X stabilizer. And every X stabilizer looks like this. So essentially, to find a logical Z, we just want to find a set of edges that hits every vertex an even number of times. A set of edges such that every vertex sees an even number of edges. And that essentially means that if we have some edge going in our logical, so if our logical operator, say, includes this edge, then it also needs to include another edge so that we have an even number of edges touching this vertex. And so essentially, for every vertex, if we have an incoming one, we need an outgoing one. And that basically means that we essentially, at this vertex again, we need another edge and so on. So essentially, our logical Z operator has to correspond to a path through this grid. It has to be a set of edges that kind of, if you enter a vertex, you also leave a vertex. So logical Z is like a path or we could even call it like a cycle. And we can try to construct this logical Z essentially by drawing a path. So we can like start somewhere and like drawing a path, making sure we're hitting each vertex an even number of times. And then we can stick like Pauli Z's on all these edges. But the problem is if we try to say this is a logical Z operator, we run into an issue because this is actually a product of stabilizers. Essentially, in these three squares, we have a stabilizer. And when we multiply these three stabilizers together, we get cancellation along each edge. Because along each edge inside here, we have Pauli Z from this stabilizer and Pauli Z from this stabilizer. And Z times Z is the identity. So if we multiply together the Z stabilizers on these three squares, we get precisely the Pauli Z's I've drawn in green. So this is just a product of stabilizers. Instead, if we want to find a true logical Z operator, we need some path that we can't just fill in with squares. Some path that's not just kind of a union of squares. And the way we can do that is actually start at the top and trace out some path to the bottom. If we stick Pauli Z's on all these edges in this path, we essentially won't be able to find any product of stabilizers that gives us Pauli Z's along this path. So this path forms a valid logical Z operator. Now we can also ask for a logical X operator. And the surface code is very symmetric between X and Z. If you kind of just dualize everything, you'll really see that it's quite symmetric. So we should expect a logical X operator to also be some path through this lattice. But this is actually where the kind of difference between the smooth and the rough boundaries come in. It's going to turn out that a logical X operator is the path going between two smooth boundaries, so from left to right. And it's also going to be a path that kind of looks like a ladder. So instead of just directly connecting edges like in the logical Z, the logical X is like, it's a sort of ladder type path. So we do tensor Pauli X's on all of these edges. And kind of this path through this lattice from smooth to smooth. But that looks like a ladder is a logical X operator. And you can check that if we take any Z stabilizer, which, for instance, if we look at this square intersects our logical X at these two vertical edges. So we have an even size intersection between our logical Z and our Z stabilizers and our logical X. So our Z stabilizers all commute with this logical X. So logical Z is also a path between smooth boundaries. And it actually turns out that this is the unique choice of logical operators up to multiplication by stabilizers. Essentially, for instance, for a logical Z, we need to take a path coming from top to bottom. And if we take any other path from top to bottom, we can kind of just multiply by a bunch of stabilizers and turn one of these paths into the other. So essentially, the surface code has one logical qubit. And the distance, which is the minimum weight of any logical operator, is the length of the shortest path either from top to bottom or from left to right. And if it's an L by L lattice, the shortest path going across the lattice is L. So our surface code has dimension 1 and distance L. And we recall that n was L squared plus L minus 1 squared. So these are the parameters we wanted. D is roughly the square root of n, and k is 1. Yes?
Why can't the logical Z operator go from smooth to smooth boundary?
Oh, yes, great question. So if we try to start here, and then we start going across, the problem is we have an X stabilizer at this vertex. And this x stabilizer will measure x, x, x. And if we have Pauli z here, then we see that this logical operator intersects this x stabilizer at just this qubit. So it will anti-commute with this x stabilizer. So essentially, this x stabilizer will give measurement outcome +1 if we tried to apply a z operator that goes in a path across in this direction.
And the logical gate has to be a combination of sets. Can it not be another?
Oh, have some x's. Yeah, so we could change our basis to have a combination of x's and z's. Yeah, so I guess the claim is that kind of the claim is that any logical operator will be essentially a linear will be either the z we found, the x we found, or some product of those two, along with some stabilizers.
Right.
I guess I haven't formally proven that, but
Yeah. Thank you.
yes.
What are the use case advantages of using this kind of setup versus a Tory code type setup where you have x and z completely dual?
Between this and, sorry, what was
Like x and z completely dual in the Tory code. So like, what's the advantage of doing this? Because it feels more natural to have a more dual setup.
Yeah, like the Tor code. Yeah, so I think this setup, one nice thing is it's entirely two-dimensional. Like the toric code, I guess you can project it onto 2D, but if we just have like a totally flat lattice, like of superconducting qubits, I think this type of setup is just easier to implement physically. But yeah, the toric code is probably more intuitive. Great, so maybe in the last few minutes, I'll there's a bunch of topics that are important in quantum error correction that, of course, we can't cover everything this tutorial, but I'll at least kind of mention a few topics that we'll see more details on later this week. Maybe one last thing I'll say about kind of the surface code and things we've seen so far is you can ask, like, what should we expect errors to look like in practice? Up until now, we've just kind of assumed that some number of errors happen less than half the distance, and then we can correct them. But in practice, a reasonable assumption might be something like that we assume errors are random. Maybe even just independent and random acting on different qubits. That's, of course, in practice, there will be some correlations, but maybe it's not totally wild to think that errors are just independent random, say probability p on each qubit. And then one funny thing is that the expected number of errors in this case is equal to n times p, which if p is a constant is linear in n, which is much greater than our surface code distance, which is square root of n. So how can we hope to correct even just random errors happening with some probability? Well, there's actually basically two solutions. There's two ways to address this. One is that kind of randomness is structured. So for a distance d code, we basically said that in the worst case, we can always correct an error of weight d minus 1 over 2. But it might be that if the errors are totally random, then with high probability, so not always, but in most cases, we can still correct a linear number of random errors. And in particular, this is, for instance, true for the surface code. For any error probability below some number called a threshold. So essentially, once the error rate goes below some threshold, which ideally will be a constant, like for the surface code, all of a sudden we can, with high probability, correct errors that occur independently with probability p. The intuition for this, kind of, if you just look at even a classical repetition code, say we have like n zeros, then if kind of random errors are happening, the only way we can't correct So some of these get flipped to 1. The only way we can't recover the original 0 is if more than half of these get flipped. And if the chance of a flip is fairly small, there's a much, much smaller chance that more than half of these get flipped. And so a kind of similar phenomenon goes on with the surface code. And it turns out that for some threshold, which some estimates have it at around like 1%, again, that's a very noisy number, but for somewhere on the order of magnitude of like 1%, 0.1% or something like that, we can correct even random errors with high probability. Though, of course, there's also the possibility that we have like highly correlated errors. And in this case, we could really just want codes of distance much greater than root n. We could even hope to have distance like growing linearly in n. And when you hear about like good quantum LDPC codes, this is kind of an area that's been very active in recent years. It's really finding alternatives to the surface code, still with low stabilizer weight, so that it's easy to measure the stabilizers, but such that the distance is much higher, like even as high as linear in the block length. So kind of this is a topic which I think we'll hear about later in Yufei's talk. I maybe want to mention kind of one more topic, which is something we didn't have time to get to, but is very important, and I think we'll hear about it later this week. And this is the topic of doing fault-tolerant computation. So I'll just write a few words, and then we can go to lunch. So fault-tolerant computation. So essentially, everything we've seen so far is about storage. We've seen how can we like take a quantum state and encode it such that even if errors happen, we can recover the original quantum state. We've only seen computation in the context of logical X and logical Z operators. This basically told us how can we do a logical X gate on our logical qubit without decoding and then re-encoding? Or how can we do a logical Z gate? And the study of fault-tolerant computation kind of takes this and asks how can we take this to an extreme where we want to do arbitrary like universal gates or universal computation on our encoded quantum state without ever needing to decode and expose our qubits to errors. And this is like a very interesting area. There's a lot of really interesting work there. There's some barriers. For instance, there's something called the like Easton-Nil theorem, which essentially says that like these X bar and Z bar, logical X and logical Z, are nice because they kind of act on all the qubits independently. This is a very nice property for fault-tolerant computation because it means you kind of won't spread errors between the different qubits. Somehow we can't get a universal gate set of these consisting of just these transversal gates. So maybe I'll just write Easton-Nil theorem. So this is just kind of some results saying like we can't hope to have perform all of our universal gates just by acting on like one qubit at a time without kind of interacting different qubits within the same code block. And there's a number of techniques that people have developed to kind of still do universal computation in light of this Easton-Nil theorem. And so if you've heard of the word like transversal gates, so these are essentially things like logical X and Z that only act on essentially one qubit position at a time. They don't interact different qubits. So that's one technique. We can do some gates like that, but we can't do like universal gates like that. Another technique to try to get around this is to use what's called code switching, where we switch between different codes, where these different codes are each good at doing different gates. So maybe we have one code that's really good at a C0 gate, one code that's really good at a T gate. If we can switch between these codes, we can do universal computation. And maybe the last technique I'll mention is what's called like gate teleportation. Or combined with magic state distillation. And this is essentially the idea here is if we have some gates, for instance, a T gate turns out to be very hard to do quantumly, we can essentially distill out some very special states that then allow us to teleport in this gate using easier gates combined with this special state. And so I guess I'm kind of just putting these words up here so that you're kind of, I guess, just have a sense when you see them, like these have to do with fault-tolerant computation. I'm sure we'll hear more about some of these things later this week. But with that, I'll wrap up.